I'm Anil Kumar. Welcome to my series on pre-calculus. In this particular video, we'll take a description of a function from its graph. As you can see, we have two graphs here. We'll try to understand how to describe them. Let me first list all the characteristics which are key or very important for us to understand. We should begin with things like domain and range for any particular function, right? So let me write them down. So we should know what the domain is and what the range is for any given function, especially when we are given a graph. Now, once we know domain and range, we can get into characteristics like what you can read straight away. So you could read x-intercept. You could also read y-intercept. X-intercept is a point where the graph crosses x-axis. Y-intercept is a point where it crosses the y-axis. Domain is all set of real numbers in this case, where the graph of the function domain is the x values which the function can take. You can say the inputs, and range is all possible outputs for the function. The other characteristics could be end behavior. End behavior really means what happens to the function when x approaches very large negative value and what happens when x approaches very large positive value. That is what happens at the ends, right? So that is these two parts. We are going to answer all these questions later, but let's understand what we are getting into. And then we can also look into few important intervals. Intervals for where the function is increasing, where is it decreasing, where is it positive, and where it is negative. So these are important intervals to look into. At times, we will be interested in rate of change also. So we normally say instantaneous rate of change. That is the slope at any point, right? So that helps us to find how fast or rapidly the value of the function is changing at any given point. Now, if possible, we could also provide equation from a graph. Well, that is not a must, but equation if possible. At times, it may be very difficult, right? So, not necessary, right? So that is how we could see it. Now, the other things which you can see is the turning points. Wherever the graph turns, we call them turning points. And these turning points lead to local or absolute maximum and minimum values. So we'll write turning points here. And those could be divided into two categories, which I'll mention as maximum or minimum value. So every turning point will lead to maximum and minimum value. At times, we will be interested in concavity of the graph. Right. So these are the characteristics which we are normally looking into when we see a graph. Now let's begin with the very first one, which looks like a cubic function. So at times, it is a good idea to provide name and some description. Not necessary, but it is kind of good. For example, in this case, we know it's a cubic function, so we could write this as a cubic function. Domain is x belongs to real numbers. Range, in this case, there is no restriction. Y belongs to real numbers. X-intercepts are the points where the graph crosses the x-axis. In this case, the x-intercepts are at x equal to -1, 0, and +1. The y-intercept is at origin, so you can say at y equals to 0. So basically, the origin, which is 0, 0, is both x and y intercept in this particular case. End behavior. When x approaches negative infinity, that is towards this side, y value, as you can see, approaches negative infinity. So in this case, y approaches negative infinity. When x approaches positive infinity, y approaches positive infinity. Quadrant 1 it is getting into, right? So this graph moves from quadrant 3 to 1. Do you see that? Now, intervals of increasing, as you can see, it increases. We have to see the graph from left to right. Remember that. So whenever you are describing a graph, always look from left to right. So if you see from here, it increases. Do you see? Up to this point, decreases and then again increases. So these are the intervals of increasing. Let me label this point as -half and the other point here as half. In that case, it increases from -infinity to -half. And then again, so we can write union, from half to infinity. Interval for decreasing is in between -half to half. Positive. Positive means when is this function, we could write f of x here. When is this function f of x greater than 0? That is positive. It is positive between 1 and 0. So we'll write this as between -1 and 0, union 1 and infinity, right? -1 and 0 and from 1 to infinity. Negative means when is this function less than 0? It is 0 from -infinity to -1. So let's write -infinity to -1 and then from 0 to 1. So union 0 to 1. Now you can never include negative infinity or positive infinity. So you'll always have this kind of a bracket here. Instantaneous rate of change. Now instantaneous rate of change is positive when the slope is like going up, increasing. So we see that from here to here, it is increasing. Do you see that? So it is positive from here to here. So it is positive when it is increasing. So these two things are linked. Positive whenever it is increasing. So that is this interval. Is it okay? And let me write here negative. Let me show it with a different color so that you can correlate the two, right? So negative when it is decreasing. When the function is decreasing, instantaneous rate of change is decreasing, is negative, right? So this portion is negative. You get it. So negative, it is from -half to half. Now another important point is where it is 0. So it is 0 at the 2 points where it turns. So the slope is 0 at the turning points, which are these 2 points for us. And these points are ±half. Now this is a very critical point to understand. Wherever the graph turns, at that point, we could have local maximum or local minimum, right? So in this case, we have a local maximum here. and local minimum at plus and minus half. We have those local maximum and local minimum, correct? So we'll skip the equation part and move to turning points, which we are discussing. So what we notice here, that it turns at minus half, and all the values very near to that are lower than the value at x equals to minus half. So that is local maximum. So we have local maximum at x equals to minus half, and we have local minimum at x equals to half. Does make sense? Now these are two very important points to be discussed when you are describing a graph. Now comes concavity. So this portion where we have this local maximum up to 0, we'll call this as concave down. It kind of opens downwards, right? So concavity is mentioned as concave down. In our case, it is from minus infinity to 0. Now at 0, concavity changes and it becomes concave up, right? So the other characteristic is concave up, and that is from 0 to positive infinity. Now local minimum is in that region where it is concave up. Point of inflection is the point where the concavity changes. So sometimes you could describe point of inflection also. So let me include that. So point of inflection, it is at origin in our case. That is at 0, 0, right? Where concavity changes. Does it make sense? So these are major characteristics which are valid for our function, right? So we describe the name, which is a cubic function, different kinds of, we describe named after that domain range, intercepts x and y, end behavior, what happens when x approaches negative infinity and what happens when x approaches positive infinity, intervals for decreasing, increasing, when is the function positive, means above x-axis, when is it negative, below x-axis, and then we looked into instantaneous rate of change, which tells you how fast it changes. Now that brings us to turning points where the instantaneous rate of change is 0. So at these turning points, we could have local maximum and minimums, right? So we could have local maximum and local minimum at the turning points. Now, wherever there will be local maximum minimum, we can look for concavity also. So in general, local maximum will be when the graph is opening downwards, as shown here, and local minimum will be when the graph opens upwards. Now, all these characteristics are the ones which are common to most of the graphs. Sometimes we have some special characteristics which we see here. Now there are different types of discontinuities which we will discuss with the second graph. So now we'll look into the second graph and again describe all those features. Mainly, I'm going to describe two particular characteristics here. One is the horizontal asymptote, and the other one is vertical asymptote. Horizontal asymptote, as you can see, is where the function approaches but is never there. Vertical asymptote is the value which is not in the domain of the function, but the function is approaching infinitely large value, right? So now let's focus on this second graph and understand how to describe such graphs. Now let us try to describe the characteristics of the graph before us. Well, you know most of them, so you can actually pause the video, describe the characteristics, and then look into my suggestions. Let's begin with domain and range. So in this case, what is domain and what is range? You can take this as your test question, right? So what you notice here is that x belongs to real numbers. However, x is not equal to some values, and the one which it is not equal to is 4. So the print is kind of smaller. This is number 4. Range. As far as the range is concerned, we can see that x with the y value belongs to real numbers. So all real numbers. We do have, it looks like it will not be this, but it crosses the value 1 right there, right? So the range is all real numbers. Now let's look into the x and y intercepts. So what is the x-intercept? And then we'll look into the y-intercept. X-intercept is a point where it crosses x-axis. Y-intercept is also a point where it crosses y-axis. In this case, both are at origin. So x equals to 0, y equals to 0. At origin, it crosses both the x and y axis. Now let's look into end behavior. That is to say, what happens when x approaches negative infinity and what happens when x approaches positive infinity. So as you can see, when x approaches negative infinity, the graph is approaching the value 1, right? So y equals to 1. Do you see that? So we have y equals to 1 when x approaches negative infinity. Now when x is approaching positive infinity, in that case also y is approaching, approaching 1, right? I should write y approaches 1. So it is not right there, but it is approaching this value, y equals to 1. Now by definition, this is called horizontal asymptote. So horizontal asymptote will be y equals to 1. By definition, horizontal asymptote is the value where the function is approaching as x approaches positive or negative large value, right? So that becomes the horizontal asymptote. Now, since we're talking about asymptote, let's talk about vertical asymptote also. Earlier, the cubic function, we didn't have horizontal and vertical asymptotes since that was a continuous function. And here there are breaks. It is kind of approaching, right? Well, in continuous functions also, we could have horizontal asymptote. That's a different story. Anyway, vertical asymptote is a value which when x approaches that value, in this case, when x approaches 4, you see y approaches positive infinity, right? From the other side also, it approaches positive infinity. So when x approaches 4 from both sides, plus or minus, both sides means from left or right, we see y approaches infinity. So x equals to 4 is not in the domain as we have mentioned earlier, but x equals to 4 is called the vertical asymptote. So the equation of vertical asymptote is x equals to 4. So this line is x equals to 4. So these two are critical characteristics of the given function which were not there for the polynomial, correct? Now other things are very clear. So let's now do intervals. So first one, increasing. It is increasing from 0 to 4, right? So it is increasing from 0 to 4. Decreasing. We can write here, decreasing. It is decreasing from negative infinity to 0 and then from 4 to positive infinity. Now, when is the function positive? So we see that it is non-negative all throughout, right? So you could write function is non-negative in its domain. Does it make sense? So you could describe like this also, that characteristics. Now, there is a critical point and we do have a local maximum. So we have a local, which is also in this case actually absolute value, absolute minimum value. At origin. So that becomes the local minimum, right? Now, in this particular graph, as far as concavity is concerned, let's look into that part. We'll consider concave up in the interval from 0 to 4 and also from 4 to infinity, right? It opens kind of upwards, right? So it is concave up from 0 to 4 and then from 4 to infinity. Concave down from minus infinity to 0. Now in this particular case, we do not have any point of inflection. That's kind of important to understand. The concavity changes, however, we do not have a point of inflection here. It is kind of a sharp corner here, right? So that makes all the difference. So we'll understand more about this aspect later, but it's kind of unique to this particular function. But I hope with this, you have clear idea of describing graph of your functions. It's a very important thing. Feel free to write your comments and share your views. Take a few examples and try to describe them. Let me give you one as a test question for you, which is slightly different from what we have done, but it will be helpful if you could look some of my videos and then understand how to describe such functions. So we'll have a sine graph, for example, right? So this is a sinusoidal function which is periodic and it repeats. Describe this graph. You know the maximum minimum values for this graph is +1 and -1. So try to describe this particular graph which has the x-intercepts odd multiples. Let me write 2 pi here. 0 pi, 2 pi, and at pi by 2 we have local maximum, minus pi by 2 we have local minimum, right? Anyway, what I'm trying to say is try to describe sinusoidal function and also try to get into, I should not write cosine here, otherwise you'll get more confused. Anyway, so I hope you understand and appreciate what we have done here. These are a few important characteristics common to most of the graphs. Explore and get ready for calculus. Thanks for watching and all the best.